discuss some of the theory that's around for coordinate descent, let me preface by saying that if you pick up any paper in the literature that has the words coordinate descent in the title, it may be talking about the method that we just learned, maybe talking about this method. It's actually unclear until you read it. Unfortunately, they're both referred to as coordinate descent. So if I had a smooth function, and instead of performing exact minimizations with respect to every variable one at a time, if all I did was take a gradient step with respect to each component, so this is actually like doing, in other words, instead of performing an exact minimization over this function, which is only a function of x1, if I just took a derivative with respect to x1 and took one step in the direction of the negative derivative, okay, that's like one step of gradient descent applied to that minimization over x1, and then moved on and did one step of gradient descent applied to the minimization over x2. That's also called coordinate descent. Okay, so that's what I'm doing here. I'm just taking gradient steps with respect to coordinates one at a time. Now, it makes sense that this is called coordinate descent because it has a flavor of a descent method just like gradient descent does, but it's unfortunate that those names collide. So what can we say about this method? Well, we're going to see in the next two slides that there's theory available for both this method and what we called coordinate descent previously. And to try to differentiate the two, I'm going to call the former, the one we learned at the start of the lecture, exact coordinate-wise minimization. Okay, because we're performing exact minimization at every step. Before we talk about any theory, which doesn't really precisely differentiate these two, by the way, what can we say about these two methods at a high level? Well, the first is this method here, this coordinate descent method, it's much more widely applicable than the one we learned at the start of the lecture, right? Than exact coordinate-wise minimization. Because we don't have to know how to perform exact minimization over any particular variable. We just have to know the gradient of our function, which is obviously very, very general. So this is applicable to any smooth function whatsoever. How do we apply it to smooth plus separable functions, like we did with coordinate descent? Well, instead of just taking a gradient step here, we take a proximal gradient step. So I just think about, for example, if this was a one-dimensional minimization of, so if f was g plus h, h1 of x1, so it's a one-dimensional smooth function plus a one-dimensional convex but non-smooth function, then I can just take one step of proximal gradient instead. Okay, that would replace this gradient step here. I would wrap the prox of h1 around this first update here. I'd wrap the prox of h2 around this update, etc. That's how I apply it to smooth plus separable functions. Okay, so these are much more widely applicable for that reason. They don't actually require exact minimizations. They just require the gradient and knowledge of the prox. But you might think that since we are able to do exact minimizations in some problems, for those problems, we'd be much better off doing that than just taking gradient updates with potentially prox applications. Because we're using a lot more information than the function. Okay, so it's easy to believe, maybe intuitively, that when it's possible, exact coordinate-wise minimization is going to be much more efficient than just this version of coordinate descent. Okay, so does the literature match that? The answer is, roughly speaking, no. There's not a lot known about either of these methods. And I've just written down here, it's about, I don't know, maybe 7 papers in the last several years that try to analyze these two methods. And they give us some insight. So there's been a lot of progress, but it's still incomplete. And a warning is that I actually didn't update this year. There may have been papers written between, well, I wrote this in the spring of 2015. So between then and now, that's been 6 months. There could have been more papers written. So this may not be the latest and the greatest. So let's go back, super far back, and just say that if you're thinking about solving linear systems with either Gauss-Seidel or Jacobi methods, which are coordinate descent methods applied to a particular loss, then a lot is known about that. That's a very classic topic in optimization. And for example, you can take a look at this book by Gauld and Van Loan on matrix computations. It gives you very precise convergence bounds for that. Okay, and then there's some interesting recent work. Actually, this is one of the convex optimization TAs from a few years ago. Aditya Ramdas. He has some nice, few nice papers on coordinate descent for linear systems that kind of provides a modern twist to Gauss-Seidel or Jacobi methods, where he looks at randomization and the role of randomization. Okay, in 2010, Nesterov wrote a pretty influential paper about coordinate descent and started off, sparked a bunch of interest in the topic, just like he did with acceleration and other things before that, interior point methods. So he's clearly a regular when it comes to kind of writing influential papers. And what he showed is that if you looked at coordinate descent, this is, so in these slides, in this slide and the next, where I say coordinate descent, I really mean descent, like this version. And if I say exact minimization, I mean the version we learned at the start. So Nesterov looked at coordinate descent, and he shows that if you're just looking at minimizing a smooth function, then you get basically the same thing you get from gradient descent. You get a 1 over epsilon convergence rate over when the gradient is Lipschitz, and that's in terms of number of cycles required. And you get a log 1 over epsilon rate under strong convexity. Okay, so you get basically the same results you get for gradient descent in terms of cycles for smooth functions. This paper was influential. It was also somewhat misleading, because it told us that, according to this paper, doing greedy selection of coordinates didn't get you anything. So Nesterov had two analyses. He had one for randomized selection of coordinates. He had another where actually coordinates were greedily selected based on a criterion called the Gauss-Southwell criterion. It's basically you just look at which component of the gradient is biggest, and you take a step in the direction of that component, because you're going to make the biggest step for that variable. If you're to do that, Nesterov's analysis showed that it actually didn't give you much compared to randomized selection of coordinates, and so he concluded that that wasn't very useful. Okay, there's a recent paper that I referenced in the next slide that actually shows that that's not quite the case with a more careful analysis. Yeah, randomized means I permute the coordinates and I take a cycle in that order, for example. So then Richtrik and, I don't know how to pronounce his or her name, Takak? I'm not sure that's right. A year after, they basically took Nesterov's results and they extended them to proximal, to the proximal version where I do smooth plus separable. Okay, so basically now, up until this point, we are saying that if I were to do a smooth plus separable minimization with coordinate descent, then I get the same things that I get out of proximal gradient descent. I get the same rates under the same conditions. So cycles of coordinate descent are equivalent to iterations of proximal gradient descent for those problems. Okay, and this is still looking at a randomized order of coordinates. Okay, I think actually this paper in some ways it simplifies even the smooth case, so maybe it's easier to read in that sense. Okay, this was the first paper that I know of by Saha and Tiwari that considers cyclic coordinate descent. It actually considers, well, it's unique in two ways. It considers a cyclic treatment of coordinates, so you pass through the coordinates in some prescribed order. And they actually consider exact coordinate-wise minimization, not just coordinate descent. So this paper is unique in both those regards. And they show that for a certain class of problems, if you do gradient descent and you do cyclic coordinate minimization, so exact coordinate minimization, then every cycle of gradient descent is dominated by every iteration of gradient descent is dominated by every cycle of coordinate descent. So after 4 iterations, you are doing strictly better with cyclic coordinate minimization than you are with 4 iterations of gradient descent. After 5, it does better. After 6, it does better, etc. So it's a very strong result. They look at problems of the form smooth plus lambda times L1 norm. The difficulties in interpreting, or the issues with this paper are the difficulties in interpreting the conditions they require on G. So they're very strange conditions. It's hard to imagine these would hold in practice. Okay, so it was a very unique paper with some strong results, but has very hard to interpret conditions on G. It reduces to some conditions. For example, if you take G to be the regression loss, it implies something about the variables in the regression that's very hard to understand. Okay, few more papers. I'll maybe just jump ahead to this last one. I'll just mention, as I said, that so Nesterov in 2010 kind of got us thinking that maybe greedy selection of coordinates weren't a good idea, but a recent paper by Mark Schmidt and some other co-authors show that for some problems, greedy selection of coordinates actually does better than a randomized rule. Okay, it's just harder to analyze. So is the cyclic case. So the randomized selection of coordinates is easy to analyze because the results are usually stated in terms of average case. And somehow that kind of smooths out the difficulties you might encounter with a greedy selection rule or a cyclic rule. Okay, so this last paragraph kind of says where we are now. General rates for cyclic coordinate descent. If I just told you I had a smooth plus separable function, the smooth part was Lipschitz, the separable thing, I knew it's prox, or I was doing exact coordinate-wise minimization on those problems. Those rates really aren't well understood for general problems. For a cyclic selection of coordinates. And further unknowns are whether or not these two should behave similarly. So kind of from practical experience, the answer is no, they shouldn't, because when you're actually performing exact minimization, you can do a lot better. And lastly, it's not really known whether any of these results are tight. So any of these rates that I told you, it's not really known whether these are tight or not. Maybe it's just something about the analysis that means that it doesn't look very favorable. Maybe in practice it does a lot better, and it requires sharper theory to determine that. Okay, so I think it's both interesting, and it also moves very fast, the theory for coordinate descent. So at NIPS each year you'll see at least a couple papers with new results on coordinate descent. So in the time I have left, so all this stuff is just bonus. I wasn't expecting to get to much of this, so this is all just bonus. I may tell you a bit about the graphical lasso, coordinate descent for the graphical lasso, and then just mention in a minute or so screening rules, which screening rules they appear on your last homework. The second problem or something is about screening rules. So the graphical lasso, for those that haven't seen it, is an optimization problem of this form. It's a matrix-valued optimization problem. And let's just first read the criterion, and then I'll explain to you what it is. I'm looking at symmetric positive definite matrices. And I'm trying to optimize the following criterion over symmetric positive definite matrices. The negative log determinant of theta plus the trace of some other symmetric matrix S times theta. This is just a constant with respect to the optimization. Plus lambda times the L1 norm of theta. By this I mean it's just the sum of absolute values of the entries of theta. So it's like I took theta, I unraveled it into a big vector, and I took the L1 norm of that vector. So if you stare at this for a bit, and you've seen, you've worked with a multivariate normal distribution in some of your other classes, you would see that this part here is like the negative log likelihood associated with the multivariate Gaussian distribution. If S is my covariance matrix, and I were to think that my data were distributed according to a normal distribution, where the inverse covariance matrix I'm calling theta. So theta denotes the inverse covariance matrix in this problem. Okay, so this is like trying to fit the inverse covariance matrix by maximum likelihood estimation, or this is minimizing the negative log likelihood, but subject to, or when I add an L1 penalty on the inverse covariance, it induces sparsity in the estimated inverse covariance. So I'm doing sparse inverse covariance estimation. That's what the graphical lasso is designed for. So why would we want to do that? Now let's back up and just talk for a minute about the motivation. Let's suppose I gave you a bunch of draws from a multivariate normal distribution with mean 0 and covariance matrix sigma. Okay, I gave you n draws from that. And this was a p by p covariance matrix, so the normal distribution was living in p dimensions. If the inverse of the covariance matrix has a 0 in the ith jth spot, then kind of classic multivariate normal theory tells us that means that if I were to take my multivariate normal vector z, it's a p-dimensional vector, I'd do a condition on all of the entries of z other than the ith and jth entries, then having a 0 in the ith jth spot of the inverse covariance matrix is equivalent to zi and zj being conditionally independent. Okay, so 0 is in the covariance matrix. So if sigma ij was equal to 0, 0 is in the covariance matrix implies that zi and zj are marginally are independent without conditioning on anything. They're just independent, because for normal random vectors, uncorrelated is the same as independent. If I have a 0 in the ith j spot of the inverse covariance matrix, then it tells me that they're actually conditionally independent given the rest. Okay, so this is an interesting property of the normal distribution. And when people want to model structure between variables, they often look at the inverse covariance matrix, if they're willing to assume that their data is normally distributed. Okay, so by performing the graph colossal, by solving the graph colossal problem, we are trying to estimate an inverse covariance matrix given some data. And S here is x transpose x over n. That's the sample covariance matrix, assuming that the data were centered. And by trying to induce zeros in theta, which stands for the inverse covariance matrix, we're trying to learn that many of the components of our data, dimensions of our data, are conditionally independent given the others. That's the setup for the graph colossal. Okay, so graphical modeling, there's actually a graduate course in graphical modeling, and Eric will give you a much better treatment of this than I will. So I think that's PGMs. So if you're interested, then take that course. There are a lot of applications of this across various scientific domains. Let's just think about it purely from the perspective of optimization. Okay, so this is an L1 penalized problem where the loss is smooth and that's separable, so we could apply coordinate descent if we wanted to. First, let's take a subgradient set it equal to 0. Okay, that's what I've done here. I've differentiated the log determinant, minus log determinant, and it's actually given me minus theta inverse. That's a property of log determinant. This is the linear term. It's just trace of s theta. Its gradient is just s. And this was now lambda times a subgradient of the L1 norm of theta. I just get a matrix full of subgradients. So those are the KKT conditions. So I'm running out of time here. I think I'm going to just continue with the graph colossal and then tell you a bit about screening rules next time, just because we already have invested a bit in the graph colossal. So basically what we do in the graph colossal setup is that we think about partitioning each of these matrices as follows. I'm going to break off an upper p minus 1 by p minus 1 block of each of these matrices. Let's call this W, just for simplicity. So theta inverse we're going to call W. I'm going to break off an upper part of W, S, and capital gamma. And that's going to leave me with basically a row and column over which I want to optimize. Now, because the matrix is symmetric, those two things should have the same values. So I can just think about optimizing over that last column. What the coordinate descent strategy does for the graph colossal is that it just changes the way that you partition this matrix. So I choose p minus 1 variables. I break off the last p column of my matrix, and I try to optimize over that column alone. And then I choose another variable column to leave out. I try to optimize that over that column alone, and so on and so forth. So that actually tries to optimize over columns of theta, one at a time. But because of the symmetric structure, we have to remember that column and row actually represent the same thing. And through a little bit of manipulation, which is given on the slides, but I don't think I'll have time to go over, maybe you can just read this one sentence underneath that minimization there. To do each one of those coordinate descent substeps requires solving a lasso problem. That was the big insight for the graph colossal. That if I do coordinate descent over the graph colossal, my substeps actually reduce to lasso problems. This comes from manipulation of those KKT conditions. So the details are all on these slides. You can take a look at it if you're interested. And the way people solve graph colossal now for large problems is by doing coordinate descent and actually solving lasso problems as the inner substeps. Now, there was a bit of a scandal a few years ago where people said that, look, I'm running the graph colossal coordinate descent algorithm, and my criterion is not decreasing. What is going on? There's something wrong. And there are a few papers written about that topic. what people figured out actually is that the algorithm I described is not coordinate descent, strictly speaking, because it's doing coordinate descent on a transformation of my variable. So our optimization variable here was theta. This is actually doing coordinate descent on theta inverse. So it's not doing, which is not, blocks of theta inverse are not the same thing, or columns of theta inverse are not the same thing as columns of theta. So it's not strictly speaking doing coordinate descent on the original parameterization, it's doing coordinate descent on a reparameterization. And what was the neat insight that some people found out was that actually this is doing coordinate descent on the dual problem. So it actually has the property that the dual criterion is going to be monotone, even if the primal one isn't. Okay, so there's a bunch of interesting research relating to graphical models and coordinate descent. So check out all these references if you're interested. Okay, so if that was too fast, don't worry about it, because this is all just bonus stuff. And next time I'll give a little bit on screening rules.